Good afternoon, class. Today's fluids lecture topic is cavitation. Cavitation is the development of air bubbles in a liquid flow due to a localized drop in pressure below the liquid's vapor pressure.
Dr. Banana Bowl, why do we care?
Good question. Well, cavitation is an issue because of how the bubbles behave once they've been formed. If these bubbles were to just float away into the sunset, they wouldn't be a problem. However, when these bubbles form around a spilling propeller, turbine, or impeller, for example, they will implode against the surface, and this can cause damage. Let's demonstrate the concept with a diagram. If we have our spinning surface of the impeller, along the spinning edges is where cavitation will occur, and bubbles here can cause damage to the metal. The degree of cavitation that develops in a flow is determined by the equation for the cavitation number. Where we have the cavitation number, the reference pressure, the vapor pressure, both of the fluid velocity, and the density of the fluid. Now, you may be thinking that these bubbles are pretty harmless. In your last bubble bath, they didn't seem to be destroying anything, but these tiny cavitation bubbles can pack a tiny punch and cause some serious damage on the surfaces that they're hitting. Now, does anyone think that they know what a vortex is and how it relates to cavitation? Yes.
According to my research, I have found the blade in this blender will create a mass of whirling fluid known as vortex. Vortices have an angular velocity about an imaginary axis.
Examples of real-life vortices are tornadoes, hurricanes, whirlpools, and Jupiter's atmosphere.
This blender is a very small-scale turbine, which will demonstrate the creation of a vortex. In this case, we would have a large cavitation number due to a lower flow velocity, so we would have non-cavitating flow. If the blade was rotating faster and the water pressure was lower, we would enter the realm of cavitation flow.
Vortex cavitation can occur in a number of large-scale applications, including turbines, propellers, and impellers.
Think about the wake behind a boat. The propeller creates a vortex due to rotation, and the bubbles we see behind the boat are due to turbulent flow that comes out of this rotation. Although this is beyond our scope and budget, if you were to zoom in and slow things down, you would see cavitation occurring on the propeller. This process is well demonstrated in this next clip by Richard Hammond in the BBC's Invisible World.
This propeller is spinning so fast it vaporizes the water around the tips of the blades, creating streams of super hot bubbles. As they collapse, they release a massive wave of energy, bombarding the propeller blades.
Thank you. That very thoroughly covers the topic of cavitation and the generation of vortices. But cavitation is not unique to vortices. It can be developed whenever the liquid's pressure decreases to its vapor pressure. This can be caused by numerous things, such as pumps and the subject of net positive suction head, which we will cover in next week's pumps lecture.
Didn't like that party trick!
We've all seen the party trick when you hit the top of a carbonated drink, causing it to overflow. Well, ladies, Greta, Marjorie, similarly in this experiment, cavitation will be demonstrated using water in a glass bottle. When the top of the bottle is struck and capped, and only the sides of the bottle are held, cavitation occurs from the implosion of bubbles formed due to the development of a low-pressure area relative to the liquid, from the bottle moving downward. It yields the following effect.
That's exactly right. Thanks. And that pretty much covers our cavitation lecture. We've seen it in pumps, turbines, and other applications in the real world. Thanks, everyone.
It was good.